Let's consider the incompressible viscous flow of air between two infinitely long parallel plates separated by a distance of h. So now along the bottom plate, the velocity is going to be equal to 0. And then along the top of the plate, the velocity is going to be equal to u sub e, which is essentially the velocity at the edge of the boundary layer. And now also, throughout this problem, we're going to assume that there is no pressure gradient, such that the change in pressure with respect to x is going to be equal to 0. So now, what we can start off by doing is we can say, since the plates are infinite in length, we're going to say the velocity in the y direction is going to be equal to 0, such that we have flow in the x direction only. And then in addition to this, we'll also say that u, or the velocity distribution, is going to be a function of y only. So it's not going to depend on x at all. So then this will actually impact the x momentum equation for a boundary layer. So let's write that out real quick. So we'll say x momentum, and this equation is going to start out with the substantial derivative. So we'll have rho and then du dt, so essentially the x component of velocity, and then that'll be equal to rho times u, partial u over partial x, plus rho times v, partial u over partial y, and that'll be equal to negative dp dx, and then plus partial over partial y times mu of partial u over partial y. And then what we can do using this information above is, since we know that v is equal to 0, this term is going to drop out. And then we also know that u is only a function of y. So this term is also going to drop out. So essentially this whole term is going to be equal to 0. And then we also know that since there's no pressure gradient, dp dx, that's going to be equal to 0. So we're only left with 0 is equal to that term. So let's write that out. So we have 0 is equal to partial over partial y of mu times partial u over partial y. So then, from this, we can actually interpret that mu del u del y is going to be constant. So we can say this equals, let's say, c1. And we know this is constant because if we take the derivative of it with respect to y, or the partial derivative, we're left with 0. So that means there has to be some sort of constant in order for us to drop down to 0. So then what we can do is we can integrate mu du, and that'll be equal to c1 dy integrated. And then we'll actually be left with mu times u, which will be equal to c1 times y plus c2. So now we can actually solve this by using the boundary information that we're given. Because we know when y is equal to 0, we're going to have a 0 velocity. And then when y is equal to h, we're going to have a velocity of u sub e. So let's do that now. So we can say at y is equal to 0, u is going to be equal to 0. And then from this, so we'll get mu times 0. It's going to be equal to c1 times 0 plus c2. So we can infer that c2 is just going to be equal to 0. So we got one coefficient down. So now for the other one, we can say y is equal to h, and when y is at the height of h, u is going to be equal to u sub e. So from here, we can get mu times u sub e is going to be equal to c1 times h. Because remember, we said c2 is going to be equal to 0, so we just drop that out. And then we can rearrange some things and get that c1 is going to be equal to mu times u sub e divided by h. So then we can get our final equation for u, and that's going to be u is equal to u sub e times y divided by h. And that's part A. So now for part B, let's go review what they said. So they said if T is equal to constant, so that'll be 320 Kelvin, and then they also give us the edge velocity of 30 meters per second, and they also give the distance between the two plates as 0.01 meters. And with that information, they want us to calculate the shear stress on the top and the bottom plates. So what we can do is we can start to write out what variables they gave us just as a refresher. So T is going to be 320 Kelvin, and then U sub E is going to be equal to 30 meters per second, and then H is going to be 0.01 meters. So now what we can start off by doing for part B is we can take the derivative of U with respect to Y, and you'll see why we'll do this in a second. So if we take that derivative, we'll be left with U sub E divided by H. Now the reason we're doing this is because shear stress, that is equal to mu, or the viscosity, times du dy. So in the end, we get that the shear stress for this problem is mu times U sub E divided by H. So now we have temperature, we have U sub E, and we have H. So now what we need to find is mu. Now with mu, there's actually a relation between viscosity and temperature, and this is called Sutherland's law. So we can say, using Sutherland's law, we can get that mu in the units of kilogram per meter second is equal to 1.458. It'll be temperature in Kelvin to the 1.5 divided by the same temperature plus 110.4. And then this will be to times 10 to the negative 6. So then what we can say is with T equal to 320 Kelvin, we should get a viscosity equal to 1.94 times 10 to the negative 5 kilogram per meter second. And then now we have essentially all of the parts to actually solve for the shear stress. So we can say that tau is going to be equal to mu times U sub E divided by H, which is equal to 1.94 times 10 to the negative 5 kilogram per meter second. And then we're going to multiply by 30 meters per second divided by 0.01 meters. So in the end, we get a shear stress of approximately 5.82 times 10 to the negative 2 pascals. And then what's actually interesting is we're going to have the same shear stress on the top and the bottom because tau is actually constant here. So we'll get the same for top and bottom wall.